Welcome to the System 390 Parallel Sysplex presentation. The purpose of this presentation is to show how IBM has enhanced the S390 Sysplex for parallel processing of commercial workloads. This presentation covers the following areas. First, we describe some OLTP or online transaction processing paradigms. Next, we compare shared data and partition data system structures. We then provide performance comparisons of both shared data and partition data system structures. We describe CICS configuration definitions. And last, we describe the changes needed to an application's CICS configuration to take advantage of parallel processing. Note that when we say Sysplex in this presentation, we mean the S390 Parallel Sysplex environment with a coupling facility to allow multiple systems to share data.
This presentation describes typical OLTP paradigms and compares their advantages and disadvantages. Let's look at some of the characteristics that make up an OLTP environment. OLTP expects multiple users to access applications simultaneously. By multiple, we mean hundreds or thousands of users. Take, for example, the typical ATM or cash machine. Worldwide, thousands of people may be requesting money or checking their balances simultaneously. Users expect a fast response. They do not want to wait long to complete their transactions. OLTP applications are usually well-defined. By this we mean they utilize existing programs and the transaction type and function are predictable at any time. To provide quick response time to many applications, OLTP applications can be cloned to process many transactions in parallel. The data needed by the application must be shared, so all the application clones can access and update the current data. Because this system configuration requires multiple updates to the same data, some type of serialization is needed to provide data integrity.
Here we see a typical OLTP application. The users of the application who submit requests or transactions to get processed. The transaction manager, which determines which copy of the application program should process the request. Application programs where there are many copies or clones so multiple transactions can be processed in parallel. This type of application program is typically written by a customer. The transaction manager is a purchased product like CICS or IMS transaction manager. The database manager, which provides serialization and access to the data. Let's compare 4 different OLTP system configurations and see how an application could be implemented in each. Single system, distributed database manager, partition data, and shared data.
First, let's look at a single system implementation. Here we see the typical structure with all the components on a single system. It is represented by the blue-gray rectangle. Let's look at how this system processes transactions. A user enters a transaction which flows to the transaction manager. The transaction manager determines which application program is available and sends a transaction to it. The application program understands the request and processes it. Data is normally requested to satisfy the transaction, so the database manager is invoked to obtain the data for the application program. Now we see a second transaction coming into the system from another user. While the second transaction is accessing a section of data, the first transaction wishes to obtain the same data. The database manager must maintain data integrity, so it prevents the first transaction from obtaining the data until the second transaction is finished. Once the transactions are complete, responses can be returned to the user.
Some advantages of this single system configuration are that all of the data is directly accessible by all of the application programs. There is only one system to manage. Assuming that the system is large and fast enough to handle the workload, a single system approach can provide a fast response since everything that is needed is available on a single system.
The disadvantages of a single system approach are limited availability because there's only one system. If this system fails, access by an end user to the application terminates. To increase throughput, Application programs are typically cloned to process more transactions in parallel. At some point, the number of clones will exceed the processing power of the system. Therefore, growth is limited to a system's capacity. When this limit is reached, the processor needs to be updated. When this is no longer possible, further growth is not possible. The technology used to produce large, fast single-system processors is very costly.
Let's look at the Distributed Database Manager OLTP system configuration. Here we see a structure that utilizes several systems to provide the OLTP environment. Each system contains a transaction manager, an application program, and a database manager. These systems can be built from low-cost, general-purpose hardware. The database manager's function is split. One section exists with the application program to provide the communication interface, and the other section provides serialization and data access. This presentation shows 3 upper and 3 lower database managers. This is not a requirement. The environment could have 10 upper systems utilizing the 3 lower database managers. The upper and lower database managers are interconnected by a communication path to provide communication between the database manager sections. For performance reasons, multiple database managers are used and the database is split or partitioned. Each manager is responsible for its own portion of the database. This means that if a transaction requires data from different parts of the database, several requests to different data managers with multiple trips across the interconnect will be needed.
Now let's look at the same set of transactions we looked at for the single system environment. Notice that there has to be a defined path for the user to get to the transaction manager. This workload balancing is typically performed by the customer by designating which system the user may use. Also notice that every data access has to flow through the interconnect. The lower database managers provide serialization for the data that they control. The transactions are now complete and a response can be returned.
Some advantages of the Distributed Database Manager approach are that multiple systems exist, which help eliminate a single point of failure. When a system's capacity is reached, additional systems can be added to provide more application instances. The systems can be built from lower-cost, general-purpose hardware. If enough of them are used, they can still provide the capacity needed to run large OLTP workloads.
Some disadvantages are that each data access needs to flow over the interconnect, which causes the throughput to be limited by the speed of the interconnect. Also, the additional instructions needed to process relatively short transactions may affect performance. As the workload changes or more lower database managers are needed, the database needs to be reorganized and split. This process is costly, labor-intensive, and it's difficult to determine where to make the split. Also, in a multiple system environment, all systems must be managed efficiently in order to avoid adding complexity to the environment. Now, let's examine the partition data OLTP paradigm. Initially, we have added a transaction router. Its job is to determine which system should process a transaction. Since each section or partition of the database is managed by one database manager, it is desirable to route the transaction to the system that controls the data which would normally be needed by the transaction. Interconnection is provided to allow the transaction router to communicate with the transaction managers. For availability reasons, a database manager is normally connected to another partition of the database. If the owning database manager or the owning system fails, the backup database manager can be told to access the data. Note that both database managers cannot access the same data at the same time. One or the other must be in control.
Now let's look at the same transaction flow as before. Notice that if a transaction needs data that is not accessible from its system, the database manager sends the request over the interconnect to the owning database manager to access and return the data. This introduces overhead similar to that described previously for the distributed database manager. The user is notified when the transaction is complete. Some advantages of the partition data system structure are that performance is very good if the database is perfectly partitioned. In this case, transactions are always routed to the system that owns the data that the transaction requires. Growth is possible by adding systems. High availability as a result of providing backup paths to the DASD so system failures do not eliminate access to certain partitions of the data.
Some disadvantages of this approach are repartitioning the database can impact availability. Multiple systems have to be managed. That the job of the transaction router is complex. As certain partitions become more heavily used than others, that is, hotspots, splitting the database is required, which then changes the router's logic. Hotspots in transaction arrivals can also require that you repartition the database. Detecting and fixing these problems is labor-intensive. The router may lack sufficient information about what data a request may require, making it difficult to choose the optimum system to process the data. Addition of systems for growth causes further partitioning of the data and redefining the router logic. Again, both tasks that are labor-intensive. The router must have additional logic so that system failures cause the router to direct transactions to the system that has taken over the failing system's data partition. Also, in a multiple system environment, all systems must be managed efficiently in order to avoid adding complexity to the environment.
Finally, we will look at the shared data OLTP paradigm. Instead of the concept of an interconnect facility for the partition system structure, we have a coupling facility, which is shown in green. Sections of it are shown below the systems. The coupling facility allows applications to share data by providing fast inter-system communication and a high-performance multi-system serialization function. With this system structure, every database manager can access all of the data.
Now, let's look again at our transaction flow. When data is accessed, the database manager uses the coupling facility to serialize the data. Once the data is locked, the data can be obtained. Because the serialization service is shared by all systems, each system's database manager can provide data integrity. Again, the users are notified when the transaction is complete.
Some advantages of a shared data system structure are that all of the data is directly accessible by all of the application programs. Availability is enhanced by having multiple systems. Additions of systems for growth does not require database reorganizations or routing changes. Coupling facility services, such as a central serialization point, prevent system hopping for data access.
Some disadvantages of the shared data approach are that multiple systems have to be managed. However, it is possible to exploit the coupling facility to help manage the systems so a single system image can be presented. Systems in a shared data environment have a potential toward sympathetic failure if not implemented carefully, such that when one system fails, the other systems fail or cannot fully function.
You have now seen some typical OLTP paradigms and hopefully understand the different implementations. IBM's Sysplex environment uses the shared data paradigm for OLTP with CICS as the transaction manager. IMS Transaction Manager could have been used instead of CICS, but for purposes of this instructional presentation, we will be using CICS. IMS DB is used as the database manager. This presentation compares some of the attributes of the shared data and partition system structures. We have now seen a high-level description of 4 OLTP configurations. Let's do some further comparisons of the 2 approaches that can be used to meet the current requirements of OLTP systems for high availability, high capacity, and flexibility, partition data and shared data.
First, we'll look at some workload balancing. The colored boxes in each system represent the work that is being processed by that system. If you look at a tuned workload for a benchmark run, it is possible in both environments to keep the workload at an ideal capacity limit. There will be some fluctuation, but in general, the criteria for the benchmark can be met. But a benchmark is different than real workload. If we look at a representation of real workload, we see that with partition data, the workload can become skewed. This is caused by an abundance of transactions that need data that is supported by the one system. The ideal capacity limit is exceeded on that system, while other systems may be underutilized. The capacity is available in the configuration, but it cannot be effectively used due to the system's structure. With shared data, transactions can be routed to whichever system that currently has capacity to run the transaction. You can see that transactions that would normally go to one system are routed to others in an attempt to keep all systems equally busy.
Now let's look how these 2 system structures handle availability. Let's say a system fails and becomes unavailable. With partition data, the failing system's data has to become associated with another system. With shared data, no changes are needed. When transactions arrive for the failing system's data, the transaction must be routed to another system. For partition data, only the system that has accessibility to the data can be used. For shared data, any of the systems can be used. In essence, all systems back each other up. With partition data, if there is not enough reserve capacity to handle all of the failing system's transactions, the remaining transaction workload is delayed. In addition to its own work, each system should have enough reserve capacity to handle the system it is to recover for, so that there is no loss in throughput. This may mean that there will be an excess capacity during normal processing. For the shared data configuration, the reserve capacity for a failing system needs to be available within the configuration and not each processor. Therefore, the necessary reserve capacity is smaller per system. The total reserve capacity of all of the systems should be slightly greater than the capacity of the largest system.
We will now compare the ease of expanding or growing the 2 system structures. Let's say we want to add a system. First, we'll add a system to the partition data environment and connect it to the interconnect. This tends to be labor-intensive and may cause the existing system to be stopped during the process. Next, we need to have data assigned to the system so the existing database is split and the data is connected to the new system. The transaction router is then updated so that transactions that need to access the new partition data are routed to the new system. With shared data, the system only needs to be connected to the coupling facility and the database. This is done more automatically and in a non-disruptive manner using fiber optic technology and is not as labor-intensive as with the partition data structure. The transaction router, in conjunction with a workload manager, can then begin to route new work to the new system in the configuration. No change to the database is required.
We have now compared some of the major attributes of the shared and partition data system structures. You have seen that the shared data approach has the following important characteristics. Workload balancing can be used to avoid transaction arrival hotspots. The shared data approach can provide high availability since all systems can be used to back each other up. Each system can be configured so that they are all equally capable of running work. The process of growing the environment is easier with shared data since the database does not have to be reorganized as new systems are added. These are some of the reasons why IBM has chosen the shared data system structure for the Sysplex.
This presentation compares some of the performance attributes of the shared data and partition data system structures. Performance is a critical aspect of an OLTP environment. To be successful, technology needs to be provided in at least 3 areas. The first is buffer management. Because of the I/O disparities between DASD and processors, an efficient data buffering technique is required. The second is serialization. Data integrity and validity of the I/O buffers requires an efficient serialization mechanism. The third is efficient messaging. Each system needs an efficient way to communicate with other systems.
Let's compare the partition data and shared data OLTP system structures and see some possible implementations that address these performance factors. Note that there are many flavors to these implementations, of which this is only one. Actual implementations may differ. What we will examine is how the partition data system structure obtains data that is not local to the system running the application program, and compare this to the shared data system structure. Here we see the familiar diagrams which have been enlarged and rearranged to help in the presentation of these concepts. The application programs, the database managers, the interconnect for inter-system communication, and the coupling facility that provides communication and serialization functions.
For buffer management, the database manager needs to maintain local data buffers. In the partition data system structure, each database manager has a pool of buffers for the data it manages. In the shared data system structure, each database manager also has a pool of buffers for the data it manages. The coupling facility provides functions to allow the systems to provide buffer validity. A directory allows the coupling facility to determine which buffer managers contain a copy of a given piece of data. A local vector is maintained for each sharing system so that the local buffer manager can determine if a given piece of data is current without the need to access the coupling facility.
Also, the coupling facility can provide buffers where data can be kept so that DASD access is not needed to refresh the buffers. Since access to the coupling facility is significantly faster than DASD access, the shared data system structure is viable. To provide serialization, some type of locking mechanism is needed in both environments. For shared data, the coupling facility provides facilities to reflect the locking status to all the systems. To provide efficient messaging in either environment, the communication vehicle must be fast, since many messages will be sent between systems. For shared data, the coupling facility is used to provide the communication vehicle. Again, the major differences are that with partition data, the buffers and locks are local in scope, while with shared data, the scope is common among all systems sharing data. Now let's look at some flows through these environments to understand the different implementations. Let's assume that there are two pieces of data that the application programs will need to access: circle and square data. In the partition data system structure, the data is located on different partitions, so access is limited to the system owning the data. In the shared data system structure, all systems can access the data.
First, an application program in the partition data system structure determines if it has direct access to the square data. It does, so it sends a request to the database manager to obtain the square data. The database manager serializes the data and reads the data into a buffer. The data is then sent to the application program. Let's assume that the application program did not need to update the data. So when the application program is finished, the database manager is notified to release the square data. The database manager releases serialization but does not clear the buffer. In this way, other application programs that need the square data do not have to access DASD, so the response time is improved.
Now we will see the same flow with shared data. The square data is requested. The database manager needs to serialize the data, but it needs to determine if the data is in use by another system. The coupling facility is used to determine this. A lock is requested by accessing the coupling facility. Assuming the lock is available, the coupling facility is updated to reflect that the data is locked and a local copy of the lock is kept in the database manager.
Next, the database manager registers interest in the square data with a coupling facility. The registration process also updates the local vector to show that the data is valid. The database manager then reads the data into a buffer, and the data is sent to the application. When the application program no longer needs the data, the database manager releases a lock on the data, and the coupling facility is updated to reflect this. Again, the data is still kept in the buffer for possible future use.
Let's continue with another flow in the partition data. This time, an application program in the other system wants to obtain the square data. The request is sent to the database manager, but since the square data is not owned by the system, the database manager sends the request to the owning system. This is sometimes called a cross-system miss, which adds overhead to the processing of the request. The owning system serializes the data and returns the data from the buffer instead of having to access DASD. For shared data, the flow is the same as it was before, when the request was from the system on the right.
The database manager requests a lock by accessing the coupling facility, registers interest in the square data with the coupling facility, and updates a local vector. Data is then obtained from DASD. Notice that with partition data, the data is only in the buffers of the owning system, while with shared data, the data is in the buffers of any system that referenced the data. With shared data, the most frequently accessed data will be in the buffers of most systems, reducing the need for DASD access over time. Cross-system access will always be needed with partition data.
Looking back to the partition data, we have an application program that requests the circle data. This is also a cross-system miss, and the flow is similar to the one just seen where the left system wanted the square data. For shared data, the same flow as before is used, since the data has not been accessed on this system yet. Now the partition data application program also wants the square data. The data is currently in use, so the request is blocked until the lock is released. The same application program in the shared data system structure also wants the square data. Since this database manager does not show that the data is locked, the coupling facility is accessed to determine if another system holds serialization on the data. Since this is true, the request is blocked until the data is released. The partition data application program that obtained the square data now changes the data and wants to commit it. The modified data is given to the database manager to commit. The database manager sends the data to the owning system, which puts the new square version into the buffer. The data is then written to DASD, and serialization is released.
Once serialization for the square data is released, the blocked request can continue, and serialization is then obtained for that request, and the square data is returned to the application program. The same processing is to be performed in the shared data system structure. The square data is updated and sent to the database manager. The data is written to DASD. Additionally, the updated data is sent to the coupling facility's buffer to maintain buffer validity. The coupling facility then updates a directory by deregistering interest and indicates to each of the systems through a local vector that they no longer have a current copy in their buffers. This is commonly called buffer invalidation.
Although the square data remains in the buffer, the system on the right will not use that data the next time it checks its local buffers. Serialization for the square data is released, and the blocked request can now continue. Serialization is obtained on behalf of this request. The data is in the buffer, but the check of the vector shows that the data is invalid. Therefore, the database manager registers interest with the coupling facility and obtains the data from the cache. When the database manager has obtained the data from the coupling facility, the current data is copied into the buffer. The local vector is updated, and the data is then sent to the application program.
Back on the partition data side, we see the application program updating both the circle and the square data. When the update is complete, the data is to be committed. First, the circle data is given to the database manager. The database manager sends the data to the owning database manager, which updates its copy in the buffer. The DASD is then updated with the current data. The square data is also sent to the database manager, which updates its buffer and writes the data to DASD. Serialization for both the circle and square data is released.
If we now look at the shared data system structure, we see the circle and the square data being updated. The circle data is sent to the database manager to update the buffer and to write the data to DASD. The new circle data is sent to the coupling facility. In this example, there are no other systems using the circle data, so no buffer invalidates are performed. The square data is also given to the database manager, which performs similar processing. For the square data, another system has a local copy, so it will have to be invalidated. Serialization is released for both sets of data. The application program requests are now complete.
You can see that the data still resides in the buffers, so that future application programs have quick access to the data. We have compared some of the performance attributes of shared partition data system structures. Some of the benefits that the shared data approach has are that cross-system misses are reduced, since frequently referenced data will be in the buffers in all the systems or in the coupling facility buffers. If the coupling facility is used as a non-volatile cache, the data can be written to DASD during free cycles or when the cache becomes full. This reduces DASD I/O, since updates can be made to the cache data without any DASD access. The connections to the coupling facility are high-speed, special-purpose connections, giving improved throughput over what is currently available with interconnect technologies. This all leads to providing efficient services that are needed in a shared data system structure. These are some of the reasons why IBM has chosen the shared data system structure for the Sysplex.
This presentation provides a description of a CICS configuration. A CICS configuration normally consists of several parts. One to handle communications with its user, customer-written transactions that perform the application's function, and code used to access the databases. The configuration may also provide a temporary storage function that allows communication between different transactions. As an application grows larger and more complex, it may be necessary to separate the functions into what CICS calls regions. For example, the application could be split into Terminal Owning Region, or TOR, an Application Owning Region, or AOR. Usually the AOR also provides the temporary storage function, and a File Owning Region, or FOR. Different combinations of regions are supported by CICS, and the structure of these regions depend on the customer requirements.
When the CICS configuration is split into regions, the different regions need to communicate with each other. CICS provides a facility called Multi-Region Operation, or MRO, to support the communication when the regions are on the same system. To take advantage of the computing resources in the Parallel Sysplex, an application's CICS configuration needs to be split into regions. Generally, an application's transactions will not have to be changed, just its CICS configuration.
This presentation shows the changes that need to be made to an application's CICS configuration to run in the Sysplex environment. Here we see a representation of a current CICS application. The blue-gray rectangle represents a system or processor. To process a transaction, this application may need to access DL1, vSAN, and DB2. Right now, the application's CICS configuration consists of just two regions, an FOR for data access, and a second region that contains the TOR, AOR, and temporary storage owning region, or TSOR functions.
Before we see the changes needed for the Parallel Sysplex, let's look at how this application works today. First, let's follow the flow of a user logging on. The lines drawn here represent logical connections between the different parts. The user enters a request to log on to a CICS region by specifying the name of a particular application. This request is sent to VTAM, who then sends it to the terminal owning part of that region. The terminal owning part processes a logon request and sends an acknowledgement back to the user. The user is now logged on.
Now let's see the flow of a transaction through the application. The question flows through VTAM and the terminal owning part until it finally reaches the application owning part. To answer the question, the application finds it necessary to access all of its databases. First, the application obtains some vSAM data by asking the file owning region for the data. Since the FOR is in the same system as the rest of the application, the MRO facility of CICS is used to provide this communication. The FOR accesses the vSAM database and returns the data to the application.
Next, the application requires some DB2 data. The FOR is not used to access DB2. Instead, DB2 is invoked directly by the application. DB2 obtains the data and returns it. To complete the answer, some data from the DL1 database is needed. The FOR is again invoked, but this time to access the DL1 data. Now that the application has all the required data, an answer can be formulated and returned to the user. We've now seen a simplified example of some flows through an existing CICS application.
Now let's see what CICS configuration changes would be needed to enable the application to take advantage of the Sysplex. Changes are normally only necessary to the application's CICS configuration, not to the application itself. First, a terminal owning region needs to be created so that it is not associated with any particular application owning region. Second, since we want to share the DL1 data with other instances of the application, access to the DL1 database needs to be changed from the file owning region to IMS-DB control. The FOR is still needed to provide access to the vSAM data. And last, one of the goals of the Sysplex is to allow multiple instances or clones of the application, or an AOR, to run in parallel. To do this, the temporary stored data must be accessible from multiple AORs. Since temporary storage cannot be fully shared at this time, it must be separated into a temporary storage owning region, TSOR. The TSOR is analogous to an FOR.
We have chosen to combine the FOR and TSOR, since there will be one instance of these regions in the Sysplex. We could have left the TSOR by itself, but this would have increased the number of regions that we would have to manage. Since DB2 data cannot be fully shared at this time, we need to have the DB2 database accessed from just one system. To do this, we have created special AORs that are used for transactions that need to access DB2. These AORs will be only on the system that has DB2. Transactions that need to access DB2 will be sent to these AORs, even if they will also access DL1 or vSAM data. We now have made the basic configuration changes, so let's add a second system and see how these regions are configured across both systems.
For this presentation, we have chosen to move the terminal owning region to the second system, but we could have left it on the first system. We also moved the application owning region and copied the IMS-DB control region to the second system. IMS-DB control is needed with the DB2 AORs, since the transactions that need DB2 may also need to access DL1 data. To allow multiple systems to share the DL1 data, the IRLM part of IMS is needed to control access to the data. Another goal of the Sysplex is to not require the user to understand the application's CICS configuration or to know what instance of the application processes a request. To do this, VTAM has been enhanced to allow a user to specify a generic name for CICS terminal owning region instead of a specific region instance. This new version of VTAM will determine the best region instance to serve a user.
This structure now allows the user to clone and run multiple instances of the TORs and AORs to allow many transactions to run in parallel and to take advantage of all the processing power of the systems. What we have done for two systems can be done for many systems. This allows for even more processing power to be given to the application. Notice that access to the vSAM and DB2 data is only from the system at the bottom of the screen. We've also added a coupling facility that will be used by IRLM and DB control. IRLM will also use it to control serialization of the DL1 data, and DB control will use it for I/O buffers.
Remember that this is a simplified structure for demonstration, and we are not trying to cover all possible configurations. Now let's look at a flow of a logon request through this new configuration. Again, these lines represent logical connection paths between the parts. This time, when the user logs on, a generic name is used instead of a specific region instance. When VTAM receives the generic request, it looks for the best terminal owning region for this user to connect to. This TOR could reside on any system in the Sysplex. For simplicity, let's say that the first terminal owning region is selected by VTAM. This TOR processes the request and passes an acknowledgement back to the user.
Now that the user is logged on, let's follow some transactions. The first transaction will be one that needs to access DB2 data. The transaction is passed by VTAM to the terminal owning region that the user is logged on to. The TOR now has to select an application owning region to process this transaction. Because of the changes made to support the Parallel Sysplex, the TOR can now select any AOR in the Sysplex. The TOR contains algorithms that enable it to spread the work evenly to provide workload balancing. But since DB2 does not yet support full data sharing, the TOR must send this question to the system that has the DB2 AORs. The TOR has to be told that certain questions need to access DB2, and those questions need to get routed to DB2 AORs for processing. DB2 was accessed, and the answer is returned to the user.
Now let's look at a transaction that does not need to access DB2 data. The TOR now has to select an AOR, and this time there are no restrictions on which AOR can be used. Let's say that the front AOR on the same system as the TOR is chosen. The AOR needs to gather data from its databases to answer the question. First, some VSAM data is needed. Since this data is controlled by the file owning region on the lower system, a request is sent across systems. The application still uses the MRO interface for the communication. But under the covers, CICS has been enhanced to use the cross-system coupling facility of MVS, thereby providing a fast communication path. The file owning region gathers the VSAM data and returns it to the AOR. Now the application needs to obtain the DL1 data that is shared by all the systems. So the application asks DB Control to provide the data and ensure that the data is serialized. DB Control requests IRLM to obtain a lock to ensure serialization. IRLM goes to the coupling facility to obtain the lock and to keep track of the current lock owners. When the lock is obtained, IRLM returns an indication to IMSDB that the data is now locked. IMSDB Control can now safely obtain the DL1 data. The locked data is then returned to the AOR.
When the AOR no longer needs to have the data locked, it asks IMSDB Control to release the serialization. IMSDB goes to IRLM, which updates the coupling facility to indicate that the lock is released. An acknowledgement is then returned to the AOR. The AOR now determines the answer to the question and returns it to the user. We have now seen the basic changes that are needed to take advantage of the Sysplex. We've also seen the differences in transaction flows between today and in the Sysplex environment. The CICS Sysplex structure you've just seen provides many benefits to a CICS application. High transaction throughput by having many application instances spread over many systems. Improved availability by reducing the number of single points of failure. Continuous operations by providing the basic Sysplex structure, which allows system and application instances to be added, deleted, updated while the application continues to run. Efficient utilization of computing resources by cloning enough applications to keep the processors busy.
Simplified workload management by having the software automatically choose the best TOR and AOR to distribute the work to. Growth by providing the Sysplex structure, since application clones can be added to handle increases in transactions and systems can be added to provide increased processing power.
This concludes the System 390 Parallel Sysplex presentation. You've seen the enhancements IBM has made to the S390 Sysplex for parallel processing of commercial workloads. Thank you for watching.